So suppose we want to find the distribution of the maximum of i.i.d. random variables. The key here should be i.i.d. The reason being, if I'm going to look for the maximum of certain things, they all should come from the same population, in the sense, the same density, the same PDF. So for me to say i.i.d, they have to have identical as a strict requirement. Independence needn't be, because I could say maximum of this variable and maximum of a variable related to the first variable, but the process is going to get really complicated. So i.i.d makes things easier. Suppose x1, x2, x3, ... up to xn are i.i.d random variables. And I am going to define y to be the maximum of x1, x2, all the way up to xn. We want to find the density of y. Well, the density of y is dependent on x1, x2, and xn. So the density of y is related to the joint distribution of x1, x2, all the way up to xn. Suppose you have 100 random variables. Think about the joint distribution of 100 random variables. Well, 2 random variables, we did it last time. Uniform, plane, uniform, circle. That's just 2. If it is 3 dimensions, you'd have to sample, say, from a sphere. If it is 10 dimensions, we can't even visualize. So the more dimensions you have, things are going to get complicated. But so having a joint distribution by itself will be painful. But since I said that they are i.i.d, I can rewrite x1 as the product of the individual random variables. Since they are identical, they're all the same, so I can raise it to the power of n. So independent and identical make things easier because I can take a joint distribution that is dependent on n variables and reduce it to one density raised to the power of n. So when we have a bunch of random variables, we should use a joint distribution. But let's say if we can find this without using a joint distribution, but using the fact that they are independent and identically distributed. So I defined y to be less than or equal to y, uppercase y. That would mean the probability of the maximum of x1, x2, all the way up to xn must be less than or equal to y. Here is a question. What would that translate to in terms of x1, x2, all the way up to xn? What do you mean by that?
Because like the maximum of all those things is just going to be another x. And so it would just be x is less than or equal to y.
Just one x. What happened to the others?
Well, we're only taking one because we're looking at
No. You have m random variables, I and 3. One of them is going to be the maximum, but to decide that maximum, the others must play a role, correct? Because they are random variables. If I say x5 is the maximum, in example of n random variables, I can declare that x5 is the maximum if I looked at every other random variable also, correct? But if I did say x5 is some maximum value, that gives us information about every other random variable. Agree? Which is less than x5. They all have to be less than x5.
So it's a given statement.
It's an implied statement. Right? If I pick, one of them to be less than or equal to y, everything would be less than or equal to y. It doesn't matter which one, because they're all i.i.d. Right? So this would simply reduce to x1 less than or equal to y, x2 less than or equal to y, x3 less than or equal to y, all the way xn less than or equal to y. I could have used x, but better to use a different random variable. Since they are independent, I can write this by splitting it up using multiplication rule, because what this means is the first random variable is less than or equal to whatever y you have, the second, the third, the fourth, and all the way up to the nth. The relationship is this and that and that and so on. Since they're all independent, I can simply multiply them together. That simply is probability x less than or equal to x is simply the blank CDF of the random variable. So fx1 of y times fx2 of y dot 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 fxn of y. But then it said that they were all identical. So I can pick one of these. and raise it to the power of n. Right. You'll get the PDF. You get the PDF by taking the derivative integral derivative n times raise n minus 1. Am I done yet? Chain rule, and then multiply by the derivative of the CDF that is inside, which will simply give me fx1 of 1. Most textbooks would simply use x less than or equal to x, but this is better to see in my opinion. So that would be the density of the maximum of n i.i.d. random variables. Doesn't matter what random variable you have. This is it. Are we clear? So I started with xi being exponential 0.03. Want to know the maximum lifetime of the kittens is at most 18 years. So y would be the maximum of the lifetimes of 8 kittens. And we derived already what the CDF of the maximum is, the PDF of the maximum is. I know the CDF of one of the exponentials. So since they are i.i.d, I just plug it in and I get the CDF for the maximum. And that would also have a support y greater than 0, just like an exponential. Similar manner, I took the value of the CDF, plugged it in there with the formula that I derived, and threw in the CDF of an exponential, and I got the PDF of y. As I mentioned earlier, to do this problem, I don't need the density. I just did the density, so you know what the density is. What is that probability? Let's erase this now. So the maximum lifetime of those 8 kittens must be at most 18 years. In other words, one of the kittens lived for 18 years, the rest croak before that. Good. So what is the probability of that happening? How would I do that using the CDF? This is something you should know if you did the homework. So we just plug in the 18 for the one. We just plug in 18 up there. So 1 minus e raised minus 0.03, 18 raised 8. Which is Fy of 18. Yes. Huh? I mean, based on the information, it makes sense because the maximum lifetime of all 8 kittens must be at most 18 years. And I have exponential of 0.03. What is 1 over 0.03? 10 to 100 divided by 3. What?
1 over 3. 1 over 0.03 is 33.3 centimeters.
Is that a 3 point what?
3 centimeters.
Wow, that's a long lifetime that I picked. So they are going to live more than 18 years. So perhaps at most 20 or something would work if I had this rate slightly different. Good. Okay. So we want to know the probability that at least one of the kittens, 8 of them, lives for 25 years or longer. It's not realistic at all, but these are super cats, they live for a long time. And then they cross the rainbow bridge. So, give that one a try. Okay, so even before we start the problem, we should, kind of think about the answer quickly. That's why we have expectations to come into play. So, expectation of an exponential is 1 over lambda. So, I overestimated significantly. So, in this case, we'll come to 33.33 years. The average lifetime of said kitten. If the average lifetime of the kittens is 33.33 years, then I'm asking, well, what is the probability at least one of them survives for 25 years or longer? Then it better be a high probability, right? It can't be a small value. So even before you start the problem, if you use a bit of logic and use some easy stuff, such as the expectation, you can guess your way, unless I guess your way out of the question, unless I put things really close. So the answer, I'm expecting it to be large, but how do we go about it logically? Well, we want at least one of them to be 25 years, to live 25 years or longer. Right? That would mean we have done this before. 1 minus the probability, none of them live longer than 25 years. I'm going really easy with the equal sign here in terms of logic because this is a continuous random variable. So equal sign doesn't matter. As I went around, this is a question some of you asked and some actually wrote. Probability of y less than or equal to 25 equals 1 minus the probability of y less than or equal to 24. Are we correct if the random variables are discrete? This is wrong in this case because random variables that we have are continuous. If I write it this way, I'm ignoring everything that is between 24 and 25, which would mean 24.00001 all the way up to 24.99999. Yes.
Shouldn't the sign before this 25 be greater than equal to?
Oh, thanks. Right? So even though this logic is correct, but we can't do that with continuous random variables. Discrete, sure. None of them live longer than 25 years. simply means in the maximum of the 8 lifetimes is less than 25 years, right? Correct. Same logic, but instead of using, multiplication rule or converting this problem to a binomial, one of those, I'm using the fact that the random variables are independent, identical, and I have the distribution of the maximum of random variables. So all I have to do is 1 minus fy of 25, which is 1 minus e raised negative 0.03y raised 8, y is 25. So what do we get?
4.
So there is a 99.4% chance that at least one of them lives for 25 years or longer. Does that make sense?